Rather than continue on the one that we were finishing yesterday, and I'll probably come back to that another time. I'd like to discuss today about the conceptual design and structural system development. I think we will continue with some of the challenges that we just faced discussed. This is a tussle, I would say, between two opinions, and this has been going on for a long time. Whether the design can be based purely on engineering judgment and intuition, or do we have to follow strictly the computations and mathematics and limits and rational approaches. We started this discussion yesterday, and I would like to continue. Of course, a lot of people will debate on either side. So let me call some experts to give their opinion on this one. These two guys, you know them, right? So I would think that they are geniuses in their own right. So let's see, what do they say about this idea about rational and intuition? Because both of them are known for both creativity and rational theories. According to So, according to him, the intuitive mind is a sacred gift, and the rational mind is a servant, is a faithful servant. And we have created a society that honors the servant and has forgotten the gift. So we honor the calculations and rational a lot, but we do not, especially in the engineering community, we do not honor, or we have forgotten the gift of intuition and thinking and innovation. And about him, it's by logic we prove, but by intuition we discover. So both of these people who live far apart, and they are geniuses, and they have created so much that we rely on these days, they have almost similar opinion about logic, rationality, and intuition. Both of them seem to agree that intuition is a very important part, and logic and rational should follow. Let's see what the famous structural engineers have to say about the same topic. How many people remember Hardy Cross? Anyone, please raise hands. Cross. Yeah, of course. Boise and few people of, Hardy Cross was one of the famous engineers who introduced the moment distribution system, and we used to use that when there were no computers. This is the only method of analysis available. You could solve tall buildings, beams, frames, everything by Hardy Cross method. So Hardy Cross did a great job of providing us tools to do the analysis when there were no other things available. However, he made some very, very controversial statements. At that time, not so controversial, but now they seem controversial. And one of the statements was, he's saying that the engineer, if you read this, he says, as the design and complexity of project increased, it became desirable and even necessary to set up series of routine procedures for analysis and design. With these standardized formulas and specifications and methods, it became possible to use a greater number of men and women with less training to produce engineering works. At that time, maybe no women engineer. And then the last sentence is most surprising, and he's saying standardization has a check on fools and rascals, or set up as an intellectual assembly line has served well in the engineering works. So an instructional engineer is saying, forget about intuition, forget about
part two of
make the tables, make the rules, and make everybody follow that. And the term rascals and fools is very interesting, because fools he calls the people who just follow the rules, and rascals who try to innovate or try to break the rules. He wants to control them both by rules and regulations and formulas. And at that time, this statement was not so controversial. Now when we look back, it doesn't seem so nice. So that is the difference, how great minds have thought about innovation and about conceptual design and about rational methods. And that's how the structural engineers differ from others. So if we just continue this discussion a little bit further, if you look at the engineering curricula, we have all been trained like this. Structural engineers are trained to follow the procedures, equations, rules, and be conformists. follow the code, follow the rules, don't break the codes. We talked about it yesterday a lot. However, architects and other disciplines are encouraged to dream and to be defiant. And I think that's where the things start to become a bit different between different professionals. And then the friction starts when the architects or innovators or people who create visions meet with the people who want to follow. They always say, oh, this can't be done. It doesn't follow the rules. It doesn't follow the code. This is not possible. They start with the sentence, this is not possible. And then the other people say, why not? And then the tussle starts. So as structural engineers, I think we are looking for a way to go somewhere in between. Let me give you an example. If I have a water tank which is 6 meters by 2 meters by 3 meters, and I ask all of you, or structural engineers, even these students here who have done the engineering, and say, can you calculate the reinforcement and thickness for this tank? Most of the structural engineer would be able to or should be able to do that because they can say, oh, I will create a finite element model. In the old days, I will go to the table, I will find a bending moment in the wall, and I can calculate the reinforcement and everything, and it's fine. That's what they do. When you give them the dimensions, give them the control parameters, follow the procedures, get the answer. Second case, design the most cost-effective water tank to hold 36 cubic meters of water. Do not worry about the shape, do not worry about the material, do not worry about any limits. Just you are completely free, do whatever you like. How many of you can start this project? Because you will say, but what material should I design? What is the design criteria? What is the height proportion that I should use? And if the client says, no, there's no limit, just go, make a water tank. And most engineers will not know where to start. They will be totally lost because they're not trained to develop something without giving them clear guidelines and clear instructions or criteria. They always look for the design criteria first. But if there's no design criteria, you can't start because it could be anything. It could be circular, square, tall, short, anything. How do you do that? That is where the conceptual design comes in, and that's what separates engineers from designers and artists. Let's go to another step. If we say design the most cost-effective, beautiful, and amazing water tank to hold the same water, very few people will be able to even say, what does mean amazing water tank? What does mean beautiful water tank? Water tank is for water, you're holding water. Why does it have to be beautiful? Why should it be amazing? It's just a water tank utility. But no, it can be, it has to be. Look at this water tank. Whoever designed it, looked at the tree forms behind that, matched the form with the trees, proportions are set like that, color is set to match with the tree color, everything is really beautiful, amazing, different. So you can see it's just not just a tank, it's now a small sculpture created over there. And this requires a structural artist, not only engineer, not only designer, but an artist. So the concept design now requires more consideration, aesthetics including, color, texture including. And this is what we obviously are not, or most of us are not trained to do. However, if you start looking, it's not everyone, I said most, there are many exceptions. Structural engineering and art, if you compare the two, you will find that there are two ways that you can look at it. One is that structural engineering in art, that means use of structural engineering in creating art, like sculpture. See, what is Eiffel Tower? Who designed it? You know that, right? Of course. Eiffel, engineer. The tower is named of the engineer who designed it. The whole city of Paris is planned around that single monument or iconic structure. If you go to Paris, there's no tall building cannot be taller than Eiffel Tower because that guy designed something so symbolic, so important that city of Paris is known for that. People go, millions of people go there, take pictures, and they want to take a picture with that, and they want to see it. And if you go to France, Newlands or Paris, you won't see it, you haven't been there. So the whole city is governed by that. Golden Gate Bridge, every movie, they destroy it. X-Men, whatever movie that is, they always destroy the Golden Gate Bridge. It's so iconic. New York, the same thing. So there are these works of art created by structural engineers which have become iconic completely and without them, city or country is not identified. So there is a book that I recommend highly for everyone to read. Those of you who have not read it, please go. It's now available on internet free. The Tower and the Bridge. The New Art of Structural Engineering. It's not so old, not so new anymore. It's quite old. I read it when I was in bachelor degree, long time ago. So this is a very important book, and I recommend to all my students to always read it, because it tells us that structural engineering is much more than just calculation, and it talks about all the great structural engineers and their work and so on. So there is a sense of this, structural engineering beyond calculations, especially, and it starts with the concept design of the structure, and that's what we were talking about in this topic. Let's get back to our procedures, our process. The restaurant design process that we follow typically has this flow: architectural drawings, structural system development, preliminary sizing, material and modeling and analysis, response and design checks, detailed modeling analysis, and finally, if we want to do performance-based design. That's what we are trained, or we typically follow. And we go through these steps one by one. And sometimes we have to go up and down if something does not follow. But can we skip these 3 steps, especially in concept level development, and just go from architectural plans directly to response, estimation of response, or the final quantities even? Can we do that? Those of you who drive, I think we all drive. When I'm going in the morning from city to AIT every day, I always find some guy every day, or woman, I don't know, who passes the traffic and weaves through the traffic and overtakes everybody as if the traffic does not exist. And they seem to have some different design or driving sense that we do not have. However, if you think about it, the calculations required to make that, the spelling is here, he also drives very fast. I think he's one of those drivers that overtakes me. When we drive, when we want to overtake a car, especially on a two-way road, and if the car is coming from the other direction and there's a car behind us, and in front of us, and we want to overtake, imagine the calculations required to make that decision, and the sensors required. You need to sense the distance between you and this car, the upcoming car, the acceleration capacity of your car, the distance between velocity, everything. Still, the self-driving cars cannot drive on a two-way road because they can't do that calculation fast enough to be able to make the decision. But we always do that somehow because we have this driving sense that we've developed over the years. We can also do the same thing with design. We can develop this design sense over the years and not just rely on calculations every time. I remember when I joined my first job as a structural engineer, I was put in a design office with the structural engineering head. At that time, he had 30 years of experience. And I said, oh, somebody has 30 years of experience? There are people who have 30 years of experience? But I saw him doing the manual design of a two-story frame the same way that I was doing. He was doing the same calculations that I was doing every time. And I was wondering why after 30 years he cannot just know that because he has done it a million times in that company before. What's the difference between him and me? And he's getting 10 times more salary than me. Why can't he just go directly to the design? And I said, oh, I'm not going to do this after 30 years. I should be able to jump ahead. So we start to learn from our experience explicitly, and we develop a kind of a design sense or experience. Same thing can now be done in another way. Not everybody has that time, so we can do the same thing now by using other techniques. So from architectural to final structural response and design, we have to do the steps, but there is a way to jump directly, not for the final design, but at least for the preliminary design and concept development. And that jump is possible through many procedures. One of them we tried at AIT. There was a master thesis that we did a couple of years ago, not so long ago, and was presented in the CTBUH conference in 2015, master thesis, which is using the artificial neural networks. So what is this? Artificial neural network basically connects, it works like our brain, it connects the input to output without doing any calculation. So it has the input, it has the output, creates a relationship between them, just like we teach ourselves, the human beings teach ourselves to make decisions without doing calculation. The neural network also does the same thing. So if you give them enough data, enough training, they can learn and they can do this job. So we took 50 buildings that were already designed with the help of our colleagues in Philippines, SY Squared. We got those buildings, we have done the performance-based design, collect all the data, collect all the input, and also we have done the design, so we also know the results. And then use that information to develop the network or train the network to make that decision directly. So architectural input, great number of stories, this, and then from there directly you get the output. And basically the methodology is very long, I don't want to go into the detail. Those of you who are interested can read this paper. But the final output is that you take the architectural parameters and then you enter into the system and you can get the response parameters like modes, reinforcement, wall thickness, and all of those parameters directly without doing any calculation right away. And then we try to check, and we found that this seems to work very well. These two graphs I'm not going into too much detail. One is because you take this data from 40 buildings, then you keep another 10 buildings for testing, which have not been used for the training. That means these are new for the program. And then you say, okay, this is my new building, and for this building, we also have the answers. So we say, this is my new building, and then we enter and we check the prediction by this method against the actual use in that building. And then we see whether we can predict reliably or not. And we found that it's very, very close. So basically, for example, nature period and the reinforcement ratio, volumes, column sizes, wall thickness, the program can predict without doing any calculation. You just provide basic input and you can get the response output right away, and it's very close to the real one for those buildings that you have already done. And this is useful, especially for checking our designs to make sure that we are not. So it's like an experienced engineer sitting over you that you have not made a really big mistake, because numbers should be like this approximately based on previous experience. Or for a new building, you can go directly and do some quick designs and comparisons. So this you can check many things. You can check the area of the core, you can check the reinforcement, comparison of the actual weight per unit, so on and so forth. Many things, and you can see they're always very close. The difference is not much. And this is only based on a small number, 40, 50 buildings. If we use 100 buildings, 200 buildings, then this will become even more close. And this is what I was talking about yesterday, that now with the big data, with the cloud computing and cloud, we can do this collectively as engineers. We can put our projects, basic data on the cloud, and then the systems can learn from that data, and we can use that to predict our new design very quickly. And we can compare many alternatives, because in that case, we do not need to spend too much time for preliminary design. Once we get the final one, we can do the detail. Or we can check our design very quickly that is it reasonable numbers or not. And that is one of the advantages of using these tools. So now we're talking about the swing towards the artificial intelligence. And there are many other things in artificial intelligence that can help us in this. Because there was a time when we had time, like 30 years, 20 years to develop experience. Now we can make use of other people's experience in a systematic manner, or our own experience in a systematic manner. So we can look at the things like fuzzy logic, deep thinking, big data, data mining, artificial neural network, genetic algorithm, expert system, and so on. Of course, I don't have time to go into all of these, but let me just discuss a few of them which are related to tall building or structural design in general. So as I mentioned yesterday also, that now we are developing methods which are suitable for computers, not making programs to automate the process that we already know. So that's a major change. So now we should be developing methods which make use of the technology rather than the other way around. Historically, if you see, people have believed that things can be scaled up. So what we did on a small scale, if we just enlarged everything, all the dimensions, linearly, we will be able to do bigger structures. But that is not really true. You know, if you look at the nature, we will find that it's not true. The structure or the skeleton of a small animal and an elephant or a large animal are starkly different because the scaling doesn't work in the true sense. But people have been thinking in the past that does. Now that is not the case. And now we have these 4 commandments of tall building design. So 4 basic principles that we can follow to develop a good concept for structural system for tall buildings. Number 1 is that resist overturning forces due to lateral loads by using vertical elements placed as far as possible. And I showed you how moving the core outside rather than the center increases the efficiency by 5 times. Second one, channel the gravity loads to those vertical elements so that the overturning stresses, tension is not developed. We mentioned that yesterday also. So the vertical load should go to the lateral load resisting element so that the gravity loads can minimize the overturning effects. Then link these vertical members with each other with shear or with elements that do not have a lot of shear left, like the outriggers, like megatruss, like other things, like belts. So we link them together. And finally, resist the lateral forces with members axially loaded rather than bending. So as long as possible, avoid bending. Move it to axial forces. Truss systems, the diagonal bracings, BRBs, those sort of things. And these 4 rules, if we just think of them as the conceptual basic commandments, when we develop the systems, we are likely to come up with a good solution. So we have to look at the problem and see whether I can follow these 4 rules to develop that concept. Then we will have a chance at a good system, and then compare it quickly using some of the existing. So very quick look. I know that. How much time do I have? 5 minutes? You're going to ring the bell? I'm not even halfway through yet. 25 out of 60, 1/3. Okay, 10 minutes. Thank you very much. So I get 10 minutes. So I'm going to skip quickly from the structural system because most of you already know that. Just to emphasize that there are 3 systems that we must deal with: the gravity load resisting system, the lateral load resisting system, and the flow diaphragm. Often we forget the role of the flow diaphragm. We have found that a lot of engineers forget or miss the design of the flow diaphragm, which is very critical in tall buildings and transfer of the lateral forces, and often this is missed. So when we do the performance-based design, we find that, engineers miss the flow diaphragm completely, so the cost increases. And then say, why did performance-based design increase the cost? Because flow diaphragm was never designed in the first place. So it's important to consider all 3 systems. I'm just going to go very quickly now. Lateral load resisting system, there are many types. There are frames, moment resisting frames, shear wall interactions, frame coupled shear wall, brace frames, tubular structures, brace tubes, and so on. But most importantly, a couple of systems that are very important, the wall systems. And we have talked about the coupled shear walls yesterday and the problem of the coupler or the element that connects the 2 coupled walls. So this is very critical. Coupled walls have to work together, and that depends on the spandrel, and we mentioned about that. Core supported structures, we talked a lot about that, so I can skip that. Core supported structures are very important. Core is key, and connecting the core to outside is another key. This can be done in a number of ways. One of the projects we did was that the core was connected to the columns by a diagonal mega truss, you can say, using the partition walls as the bracing elements. So this project was in Philippines. In fact, currently the tallest building in Philippines, right, Alex? Still the tallest? Gramercy? Yeah. So we use this system in 72-story building in Philippines to brace it by using the existing partition walls and making them part of the structure by diagonally connecting them and creating a mega truss on the inside the building. So nobody knows a truss exists because we just randomly selected some of the partition walls in the floors, in the apartments, and make them in concrete so they become part of the structure and transfer the loads to the columns. Spine wall systems, outrigger and belt system, very important, very popular. The most important question is how many outriggers to use and where to place them. And this is a study that we always do for our projects to find out what is the best location of outriggers. How many outriggers to use? In fact, now we have a thesis going on this topic. So these are important questions, and the optimum location of the outriggers can significantly increase the economy as well as the performance of the structure. So this is something that we need to study. Other wall systems, tubular systems, single tube, frame tube. In fact, the difference between tube and a hollow tube or a frame is just transition. The size of the vertical members and the horizontal members. You start making them thin, it becomes a frame. You start making them thick, it becomes a wall, coupled wall. So somewhere in between there is a tube. So it's a transitional system, not a completely different system. So a complete solid wall to a complete frame, this is just a transition of the sizes of the columns and the link beams. Shear back is an important aspect that we must consider in this one. Irregular tubes, sometimes shear back can be reduced by putting the diagonals. We have seen in many buildings, we can put the tubes together, create bundle tubes when one tube is not enough. Selection of structural system, I have to go really fast now. Maybe I can discuss this. You can have these presentations later to read more detail about this one. There are many ways to do that. One of them is rich pictures. And rich pictures is in fact very important to look at the things on a big way, from the bird's eye view. Consider everything, not just structural system. That's why this seminar has many topics to give a broader view of what we want to do. Look at the knowledge models involved in design of the structures. And this is one thesis done, and Sudiksha is here, who did this thesis. She's an architect by original training. She did master's in structural engineering, so we thought she's the right person to work on this topic because an architect and structural opinions can be combined together into this rich pictures. So she developed some of this information that I'm presenting. So basically, rich pictures can really help to develop a system which serves many purposes. So these are some of the rich pictures in terms of the collaboration of various professionals, systems. We can also use another very interesting and very commonly used process called analytical hierarchy process, or AHP. We use it a lot to compare systems because you can compare the value of a system, of several systems, by single value. So it's a very simple yet rational system to compare different options. These are the way that we do that, and this is scoring, so you can read more about that. Final couple of slides, in fact, final slides is, to do a good conceptual design, we should develop the concept at a high level. Really at a high level, not only focus on one aspect. Identify the challenges and find solutions one by one. We talked about the challenges and solutions yesterday. Compare values and alternatives, value engineering, and use previous experience, the neural networks. Be innovative, be defiant, think outside the box at this point, and do not forget these guys, what they said. Thanks so much.